So far, we've just looked at circuits involving just a battery and capacitors, or just batteries and resistors. What happens if we combine the two? It turns out just arbitrarily combining them can lead to some complicated situations, so let's think about the simplest possible combination we can create. What if we had a battery, we'll call it ideal here, and say it has an EMF with no internal resistance, and we hook it up across a discharged capacitor and a resistor all in series? What would happen? We remember that if we just connect a battery to a capacitor, after a very short while, the capacitor will have completely charged up to the same voltage as the battery, and no more current will be flowing through. Really, the introduction of the resistor doesn't complicate things all that much. All it does is just slow down how fast this capacitor becomes fully charged. Eventually, current does stop, but it just takes longer in practice for the current to go to zero. But how do we quantify all this? Well, we can't use any series or parallel relationships we've built up because we only have one of each component. We have one resistor and one capacitor. But we went over Kirchhoff's laws in the previous lesson, so maybe they can help us out here. We can't use the junction rule because there are just no junctions, but we can use the loop rule on just this single loop. Maybe that'll be insightful. We know in advance because the capacitor starts out empty and because of the orientation of the battery that the current has to flow from the positive terminal to the negative terminal. In passing our finger along the battery then, we have a positive change in potential because we're moving from the negative terminal to the positive terminal. So we jump in potential by an amount of the positive EMF. Then because the current is flowing this way, positive charge is going to build up on the bottom side of the capacitor, and negative charge is going to build up to counter on the top side. So actually, in moving our finger across the capacitor here, we have a negative potential difference because the positive plate is at a higher potential than the negative plate. But also, we know by now that we can write the magnitude of the potential difference across the capacitor as Q over C, where Q is the charge on one of the plates. Then here we can say we have minus Q over C as the potential difference, where we've written Q as lowercase to indicate that it's changing as the circuit is operating. Now finally, across the resistor we expect a negative potential difference because our finger is moving in the same direction as the current, so we expect the potential to drop. In that case, we can say that the potential difference is minus I times R, where we have lowercase I to indicate that actually the current is changing as well. The current isn't really constant here. And that's our last element for the loop rule. We're back to where we started. So summing them all together gives us 0. Now we're in a weird situation. Assuming the EMF, capacitance, and resistance are all known to us, we have one equation here. With two unknowns in lowercase, we have Q, the charge on a single plate of the capacitor, and I, the current going through the whole circuit. It's not immediately obvious how we make progress from here, so why don't we just try something out? Let's solve for the current I. In order to do that, we just add IR on both sides and then just divide by R, and we're left with this equation here. Now we have the current going through the entire circuit as a function of just the charge on the capacitor, so we can actually use this single equation to come to some neat conclusions. For one, what's going on at t equals 0, meaning when we have a discharged capacitor and as soon as everything is connected? Well, at t equals 0, there is no charge on the capacitor yet, so Q equals 0 as well. In that case, the current is just the EMF divided by the resistance. We also know that this is the current that we would experience in the circuit if there were just no capacitor in it at all. So our current starts out at I equals the EMF over R, and eventually goes to 0 once the capacitor is fully charged up. So what can we say after a long time when the current eventually becomes 0? If the current is 0, then the capacitor is fully charged up, so it has its maximum charge at that point when there's no more current flowing. What we see then is the max charge on the capacitor is just given by the capacitance times the EMF, which kind of makes some sense too, right? If we consider the EMF as the voltage across the battery, we expect that voltage to eventually be the same as the voltage across the capacitor once the current goes to zero. Since the voltage across the resistor must be zero because I is zero, and that matches our Q equals C times delta V equations that we were dealing with before. So there's a weird sort of duality at play here. At t equals 0, it's as if the uncharged capacitor doesn't exist in the circuit at all. There's no potential difference across the capacitor, and all of the battery's potential difference goes exclusively to the resistor. After a long time, though, we have the opposite situation. It's as if the resistor doesn't exist in the circuit, and there's no potential difference across it, since I equals 0, and all of the battery's potential difference goes exclusively to the capacitor. So we've actually been able to say quite a lot about this single equation, despite that we have two unknowns. But we can do better. We have current and charge in the same equation, and in general we can relate the two with the calculus definition of current. The current in the circuit is the instantaneous rate of change of the charge across some cross-section. In this case, we're considering the charge on the capacitor, but the idea is the same here. We can kinda treat the capacitor as our imaginary cross-section. So plugging this in, we have this equation here. The rate of change of the charge with respect to time is equal to E over R minus Q over RC. Now our only unknowns are Q itself and the derivative of Q with respect to time. This is called a differential equation, or an equation which involves only some function and derivatives of that function. Here that function we're referring to is Q, the charge as a function of time. Many differential equations are unsolved to date, but this one we can actually solve with not too much effort. But at the risk of alienating the non-calc peeps, we've just left the solution for this differential equation in the next video for the calculus peeps. What we find when we solve out this equation is the charge on the capacitor as a function of time is given by C times the EMF, all times 1 minus e to the negative t over RC. Quite a peculiar expression, so what does it look like on a graph? We see that as t approaches infinity, the charge on the capacitor asymptotically approaches to some maximum value, which we said before was the capacitance times the EMF. Now we can go even further with this idea. If we take the derivative of this expression with respect to time, we should get the current as a function of time. So we'll leave that computation for the next video if you're interested, but it ends up coming out to the EMF over R times e to the negative t over RC. This is also quite a peculiar equation, so what does this look like on a graph? We see when t is 0, e to the 0 is just 1. So the current starts out at a value of the EMF over R, but over time as the capacitor becomes more and more saturated, the current exponentially decays to 0. So now we have a situation where the current is actually changing as a function of time. It's not constant like we've assumed in all of our previous discussions with resistors, where we've been assuming steady state conditions. Now frequently, when dealing with physical systems, we run into expressions of the form e to the negative t over tau. Whenever we have expressions that can be written as an exponential decay like this, tau is called the time constant, and it's useful here to figure out what our time constant for this RC circuit is. Because our expressions are in the form e to the negative t over RC, we see that our time constant is just R times C, the resistance of the resistor times the capacitance of the lone capacitor. And that's actually where the name RC circuit comes from. That gives us the ability to rewrite our current charging and current discharging equations. Now, why should we define something like this? Well, the reason it's useful is because it gives us an easy way to visualize how long it'll actually take for the circuit to run its course. What I mean by that is the time constant actually has units of seconds. Yes, if you multiply out ohms with farads, amazingly, you end up with just seconds once you go through all the motions. An ohm is just a volt per ampere, and a farad is just a coulomb per volt. The volts cancel and we're left with coulomb per ampere, which is just coulomb per coulomb per second, or just seconds. So assuming we know the resistance and capacitance, the time constant is just the two multiplied together. So let's see how that helps us. If the units for tau are seconds, we can actually mark our t-axis in terms of tau increments. What is the charge on the capacitor when the time elapsed t is equal to a single time constant tau? Then we just have c times the EMF, all times 1 minus e to the negative tau over tau, or just 1 minus e to the negative 1. This is about 63.2% of the max charge that'll end up on the capacitor. What if we weigh two time constants, or 2 tau? What's the charge then? The charge on the capacitor is about 86.5% of its maximum value. We can keep doing this for any value we choose for tau, and what we find is that after around 5 tau have passed, the capacitor is nearly fully charged. We see 99.3% fully charged. And even up to only 8 tau, we have the charge on the capacitor as 99.97% its max charge. It's basically fully charged at that point. So when someone else looks at this graph of the charge versus time asymptotically reaching the maximum charge, they'd be like, well, actually, the charge on the capacitor never reaches its maximum value. It just approaches it as t approaches infinity. But we now know that in practice, really just after 5 tau, where we can determine tau in advance, we already know what tau is, the capacitor is pretty much fully charged. Or if that's not good enough, just to be safe, after say 8 tau or 10 tau, for sure it's fully charged. If that still upsets you, you can always just wait a little longer. Now we only talked about the charging scenario, which landed us at this differential equation, which had these solutions for the charge on the capacitor and the current through the circuit as a function of time. But we never talked about a very similar situation, which is what if we charge up a capacitor to some charge, and then we remove the EMF and just connect it across a resistor? This results in the capacitor discharging all of its charge through the resistor. Now the loop rule applied to this circuit looks like this. I encourage you to work it out yourself if you like by tracing your finger around. Now there's a bit of an awkward moment here in that we have to define the current I here as negative dq by dt. The reason why is, even though in general dq by dt is what we refer to as the instantaneous current, here we're using dq by dt to refer to the rate of change of charge on the capacitor. And we know since the capacitor is discharging, the charge on the capacitor is decreasing, so the rate of change of charge on the capacitor should be negative. Then in order to keep the current positive, because we already know the current direction is correct, we have to define I as negative dq dt here. Just an awkward sidestep, but once we have that out of the way, the differential equation is quite simple, more simple than the charging one. The solutions look kind of similar to the charging scenario too, where Q0 here is the initial charge on the capacitor. For the charge, we see instead of an exponential saturation like we had before, we have an exponential decay. And the current kind of has the same behavior in the charging and discharging scenarios, just going in the opposite direction. In the next calculus-based video, we'll see how we go from the differential equations to the solutions in both the charging and discharging scenarios. For the non-calc people, I would maybe recommend putting these equations on a formula sheet somewhere, or at least memorizing them in case you ever need them.